I will share the other screen right now. You guys can see my other screen?
Yeah, we can see it.
Thank you. Okay, so this is lab 4 now, which is just, applications for the diode. We will explore 3 applications and a problem. These 3 applications is the diode clipping circuits, the positive half-wave rectifier, and the effect of breakdown voltage of the diode in half-wave rectification. Okay. So this is basically the first application, which is a positive. This is positive clipping. Okay. So I want you to construct this circuit and set up the input with these values, 21 volt RMS. Okay. And a change VB with 3 values. Put it 10, put it 0, and put it -10. By the way, this is the homework. So in the homework VB, I asked you to solve it on the sketch the output at -2. You will do it here at -10. It doesn't matter. Okay, it's almost the same analysis. I mean, yes, of course the output will be different, but same analysis. The output will be similar, not different. Okay. And just write down your observations about this. So basically the observation is based on the value of VB. We will move up or down the clipping point. So if VB is positive, the clipping point will be in the positive half cycle. I'm sorry, it will be the clipping will happen, part of the clipping will be on the positive half cycle. Okay, if it's 0, there is no clipping, it's just 0.7. There will be a clipping, but just with the diode voltage. And if it's negative, this will be the solution for your homework. Okay. And of course, you should know by analysis without oscilloscope or multisim, you should know or expect by hand what should be the output at -10 or VB is negative in general, like the homework. Okay, so guys, open now multisim, and you have 10 minutes. After 10 minutes, I will ask you. I will just. So you guys can see my screen. So this is what I'm saying. That, for example, in that example here, that this part, for example, is exactly this one. Okay, so if you move the signal, if you move this signal, for example, down, it will, until some point, it will this dome here will become here, and you will have exactly the same as the input. Okay, so you can check on yourself by adding, and the adding should give you the same as input. Okay, which is drawn on the other oscilloscope, or you just move up and down one of the signals until you get exactly what you should get by adding them up. Okay, so this is a part of how to check your solution. Okay, and again, multisim is a very good tool, especially for this problems that I will ask you to sketch the output. Okay, if you stuck at some problem, or you solve some problem, you have something that has some doubt, just to do that using multisim. So let's go back to my multisim. Anybody has any problem with this, with experiment 1? If there is any problem, just let me know, okay? In the chat, for example. So yeah, so this is basic. So this is basically VO, and This is basically VR. So if we move VR up, for example, just like what Troy did. So let's move it up. Oops. Yeah. You know, of course, I can't control. Maybe I can. Yes, I can. Yes. So this is the, approximately. So yeah, this is the input actually. Okay. So this part here is just goes to the resistor, and the other part, this big part here, goes to the V output. Okay, enough with this. Now let's change VB. Of course, if you did the first one correct, then the other one will be correct as well. So let's do it first 0 and see. With 0, there will be still a clipping, but this clipping will be at 0.7, very small, this one. So this is the voltage on the resistor, and this is the voltage. So let's concentrate. Yeah. So the signal that we are seeing right now is the output signal. There is still clipping, but this clipping happened at 0.7, so it's really small if we compare it to the Vmax. That's why the ideal model is sometimes very useful, because if you have a very big input voltage, then this 0.7 can be neglected somehow. Okay. So if you want, show it much better. Let's yeah. So you see this is actually 0.7, but with a larger scale. So there is still clipping, but this clipping is happening at 0.7 plus 0, because VB is now 0. Now let's do.
Yeah.
Thank you. Okay, so let's go now to the next experiment, which is the positive half wave rectifier. Okay. Just guys, copy and paste from create a new project again. Okay. Copy and paste and then you remove with some stuff that you don't need, and just to keep only one diode. Where is it? Just to keep one diode and the resistor, and they change the resistor to 100 ohm and make it at the output. Okay. Make the input 110, just like the outlet in your home, with 60 hertz. Then check the output on the diode and the output on the resistor. Okay. So let's do it very quick with you. I already did it. It shouldn't take time. So this is a half wave rectifier. This is a circuit. So let's run it. So this is the output on the resistor. Only the positive halves go through, and the negative half just go to the diode. So if this is the voltage on the diode. Okay. And you can't see the 0.7. If you go back to the analysis that I did, there should be, a very small clipping at 0.7, but you can't see, because now the voltage input is 110 RMS. It's 110 square root of 2. It's 155.5. Very high compared to 0.7. So we can barely see this point. So we can't see it actually. Okay. We need, to reduce the scale very, very high to see this. This is actually 0.7. Okay. There is a clipping at 0.7. But it's really negligible. Okay, to the 155.5 volt you have. That's why the ideal model can be used, conveniently, without having any fear of having inaccuracy or something. Okay, because really the error is really small. Okay, guys. So just bring it back to what it was. Yeah. And if you move the two signals together, the VR and the VO, I'm sorry, the VR or the VO and the VD, you will get exactly the input. This is exactly the input, right? Of course, if you make add, you will, and normal again. This is exactly the input. But without making this add or stuff, just YT, but, but you just, move, or without moving, actually, here without moving. You will see that they just, attach to each other, forming very similar shape to what we have in the input. Because of course, the Kirchhoff voltage law is hold all the time. Okay, guys, try to measure the maximum here. This should be 155.5 minus 0.8 or minus 0.7, whatever. And try also to measure this clip, which is really small. Try to measure this clipping. Okay, so here it's 1 division, approximately 1 division, multiplied by 1. Good. So this is basically 1 volt. So it's not 0.8, it's not 0.7. So what's it going on here? Why it's not 0.7 like our analysis? So basically, remember, we are dealing with the constant voltage model. In the constant voltage model, we assume that whenever the diode become on, it's 0.7. Although that's not exactly the case. We saw there is a change in the voltage as well, but the voltage is still, the change in the voltage is really, really, really small. Okay, it was between 0.6 and 0.8. But if you increase the input voltage too much, then it will exceed also 0.8, no problem in that. So here, the diode, when it become on and stabilize the voltage at 1 volt. Okay, approximately 1 volt. That's why the clipping voltage is 1 volt, which is really still really very close to 0.7. And both compared to 155.5 they are both very small. Very small. Okay, so the output on the resistor, this one, should be 155.5 minus 1, because we measured now the input is the clipping volt is the VD on of the diode, and it was 1, not 0.7. Okay, so guys, do that now, and you have again 10 minutes. Nobody tell me yes.
Yeah.
Good. So the last thing we're gonna do here, we're gonna change the model or the characteristic of the diode. So let's go to examine what are the characteristics of this diode. Okay, so we're gonna go to edit model. So these are all the characteristics or the parameters that this diode have. One of them in particular is yes, breakdown knee voltage. It's a breakdown voltage. Okay, at what voltage this diode will break down. And as you see here, it's 1000 volt, very high, very high. That's why when we use a rectifying, this is called the rectifying diode. When we use a rectifying diode, we usually neglect what's happening in the negative half cycle. In the negative half cycle. We usually assume that the maximum negative voltage is always less than the breakdown voltage. Okay? But if this diode is very expensive, okay, you must take that into consideration. So let's do now a change this value. You can change it, by the way. Okay, so we're gonna make it 100. Okay, only 100. Then I don't know what. Yeah, just click and that's it. Okay, then change component. There is no okay. You should choose a change component. Now it has 100 volt for the breakdown. Okay. Okay, then so when you change some of the parameters of the diode, you see, guys, this little asterisk. There is some very small asterisk. I don't know. Yeah, you see, guys, this little asterisk. That means there is a change in the model of that diode. because we changed the breakdown voltage from 1000 to 100. Okay, so let's run and see. Oh, yes. So this is a problem now. So this is basically the half-wave rectification. There is no rectification anymore. Okay, because the diode becomes on in the reverse bias. Remember, the maximum voltage on the reverse is minus 155, which is larger than minus 100. Okay, so the diode has made a clipping at minus 100 in the reverse bias. And once it makes a clipping, that means the voltage on the diode is constant, equal to minus 100, the breakdown voltage, and the rest of the voltage, because Kirchhoff is always applicable, will go to the resistor. So the resistor, which is the load that's supposed to have only positive voltages, receives now some negative voltage. Okay, so even the 50% of rectification has gone now. Okay, so that's the problem that I was talking about yesterday, that you should take care of, or must be sure always, all the time, that the negative reverse voltage of the input is much, or less than, at least, less than the breakdown of the diode. Okay, so now you should measure this negative peak, and also measure this. So this should be minus. Let's check it. So let's confirm it's minus 100. So let's move this a little bit to right or left. Yeah, we have this guy. We have those. Good. Yeah, minus 100.4. That's, you know, can't say minus 1. That's fine. Okay. So there is, if again, the bottom line, if the maximum of the breakdown, if the breakdown voltage of the diode is less than the negative max of the input, there might be a clipping, and this is what's happening now. Okay, so it's not a half-wave rectification anymore, because some of the negative goes to the output also. Okay. So guys, do that. You have 5 minutes, because it's very easy.